Hey guys, more in chapter 5. All right, so what we're going to do today is we're going to take those two-dimensional Lewis structures that we drew and we're going to look at how they exist in 3 dimensions in real life. With this video, I assume that you guys have done your due diligence in Lewis structures, that you're comfortable with lone pairs and bonding pairs and double bonds. So in this point, I'm going to assume you know how to draw a Lewis structure, and I'm going to build upon that knowledge. All right. So predicting shapes. Here we've got 2 molecules, and they look like they should be pretty similar. So we've got carbon dioxide, so 1 carbon, 2 oxygens, carbon in the middle, oxygen on either side. We've got water, 1 oxygen, 2 hydrogens, oxygen in the middle, hydrogen on either side. So why in the world is our carbon dioxide a straight line and our water is this kind of bent structure here? Well, it has to do with something called Vespr. So what we are going to use to predict the shapes of these molecules is Vespr, valence shell electron pair repulsion. That's a lot. So it's a really heavy statement. So let's break it down. So first, valence shell electrons. Well, that shouldn't be a surprise at all. So remember that we're dealing with the electrons that are in the valence shell. Those are the only ones available for bonding. So the only ones available to be shared. Electron pair. So we're talking about pairs of electrons, lone pairs, bonding pairs. And this last part, electron pair repulsion. So what we're going to look at here is that these electron pairs are repelled by one another. So remember, they're negatively charged particles, right? So these pairs of electrons are going to try to move as far away from each other as they possibly can. So think trying to push 2 north ends of a magnet together. Those 2 north ends are going to repel each other and push away. Electron pairs are going to do the same thing. And in 3-dimensional space, they're going to try to get as far away from each other as they can. Okay. So we're going to look at electron groups on the central atom. So before we look at how these push away from each other, we need to figure out what in the world we're looking at, right? So the first thing, central atom. The central atom is going to be our pivot point. Okay, so here in this ammonia molecule here, our nitrogen is our central atom, and we're going to be looking for all the things that are around it. In this one here, we're going to have our carbon as our central atom. We see these 3 things around it. And here's our oxygen as our central atom with its bonding pairs and lone pairs. So the central atom is going to be our pivot point. We're going to look at the different types of things that are attached to the central atom. So one of the first things that we're going to look for is lone pairs. So looking at this ammonia molecule, it's going to have 1 lone pair. Looking at this oxygen atom, it's going to have 2 lone pairs. So we're going to look for and identify lone pairs. We're also going to look for and identify single bonds. So single bonds are just those 2 electrons that are being shared. Excuse me. So if we look at this oxygen atom here, we would say that it has 2 lone pairs and 2 single bonds. So a total of 4 things that are around that oxygen atom. Same thing here for the nitrogen. So 1 lone pair and 1, 2, 3 single bonds. So 3 plus the 1 lone pair, we got a total of 4 things around it. And then the last thing that we're going to consider are multiple bonds. When we're looking at multiple bonds, we're going to consider them as one thing that's attached to the central atom. So if I'm looking at this carbon atom, I would see that I've got 1, 2 single bonds, and I've got 1 multiple bond. So if I were to add up the number of things that are attached to that central atom, it would be 1, 2, 3 things that are attached. All right, so now that we know what we're looking for, and we know that we're looking at the central atom, let's take a look at how this all works. So here our central atom is beryllium. And beryllium has how many electron groups or how many things attached to it? It's got 1, 2 electron groups. So remember, we're talking about these electron groups trying to get as far away from each other as possible. So they want to get as far away from each other as possible. So what is the largest angle that 2 things can put between themselves in 3-dimensional space? Well, the largest angle that they can put between themselves is 180 degrees. So when we have our central atom and only 2 electron groups or 2 things attached to that central atom, we're going to see that it forms a straight line. It puts 180 degrees between those 2 things. Okay? This is going to be called a linear geometry. So all of the elements are in a straight line. 3 electron groups. Okay? So here's our formaldehyde molecule. Carbon is our central atom. We've got 3 things attached to our carbon here. Single bond, multiple bond, single bond. Remember, we count this multiple bond as 1 thing. So 3 things attached. The way that this is drawn in 2 dimensions is a little bit deceptive. So if I want to get the largest angle between each of those groups, what's the largest angle that I could put between 3 things? Okay. Well, it looks like I can put 180 degrees here and 90 degrees here. But if I scoot these hydrogens down a little bit more, I can get 3 identical angles between all of those groups. And I can put 120 degrees between each of those electron groups. This is called trigonal planar. So if I were to pick up this molecule and turn it on its side, what you would see is all of those atoms are in the same plane. This is a nice flat molecule, so planar, flat. And all of the atoms are in the same plane. And again, trigonal because there's 3 of them. It's kind of like a triangle. So this is our trigonal planar, 3 electron groups. The next one we're going to talk about is 4 electron groups. So here we've got methane Ch4. So this molecule, again, is drawn deceptive. In 2 dimensions, the biggest angle that we can get between those is 90 degrees. But remember, we're dealing with 3 dimensions. So if I were to pick up this molecule off the paper, put it in 3 dimensions, I can actually get an angle that's larger than 90 degrees. So here we see what's called a tetrahedral shape. So think of this as kind of like a 3 legs to a chair, kind of stands up high. There's some space underneath this carbon. And then the last one is sticking straight up in the air. Okay, so 3 pegs to a stool here, sitting up high. And then we've got the hydrogen going straight up. So 4 electron groups is going to give us a tetrahedral geometry, 109.5 degrees. Okay. So this is certainly something I'm going to ask you guys to do on an exam. We're not finished yet. We've got a lot more to talk about here. This is certainly something I'm going to ask you to do on an exam. So I may give you the formula for methane. So I may say, draw the Lewis structure for CH4 and tell me what it would look like in 3 dimensions. So you would have to come to the conclusion that that's a tetrahedral geometry. Okay. Well, something to consider here. All of the examples that we've looked at thus far have not had any lone pairs on the central atom, right? They've all been bonding pairs. Okay. So what happens when there's a lone pair on the central atom? Well, we still classify that as 4 things that are attached to the central atom. So 1, 2, 3, 4. So when we have 4 electron groups or 4 things attached to the central atom, what was our geometry for that? Yeah, it was tetrahedral, right? We had the 3 legs to the stool here and then 1 thing sticking straight up. When we have our lone pairs, what we notice here is, remember, this is an electron density, right? So it takes up kind of a volume of space. So here we see this 1 thing sticking up, and that's the lone pairs, but notice that it does take up a pretty big amount of space, okay? But when you see this molecule drawn in textbooks, we typically don't draw that lone pair of electrons. It's there, but we do not draw it when we draw the shape of a molecule. So what we're going to introduce now is a different type of geometry. So this would be the electron geometry when I take into account all of the electron groups. So there's 4 electron groups. They want to get 109.5 degrees away from each other. So we're going to have tetrahedral as our electron geometry. Our molecular geometry essentially just kind of hides the electron group. So if I took a box and put it over this electron group, this is what we would see. We would see the molecular geometry. The molecular geometry is absolutely dictated by the electron geometry. So molecular geometry in this case is trigonal pyramidal or pyramidal. So when I look at this, it's kind of like a pyramid. It's going to stick up off the table. There's going to be space underneath this nitrogen atom. It's not going to be flat touching the table. So this is trigonal pyramidal. The reason that it does have this kind of bend in it is because it's based on this tetrahedral electron geometry. So all I've done is hide the lone pair, but the lone pair still dictates what these bond angles are. Okay. So electron geometry, molecular geometry. Now we can finally see why water is always drawn as bent. So if I look at a water molecule, what does a water molecule contain? It looks like this. So it's H-O-H. And what's attached to that oxygen? Yeah, 2 lone pairs. So if I look at the number of things that are attached to this oxygen atom, I've got 1, 2, 3, 4 things attached to the oxygen atom. Remember, 4 things tells us that it is a tetrahedral geometry. Okay, so here's our tetrahedral with a roughly 109.5 degree angle. So electron geometry, tetrahedral. If I were to hide those lone pairs, what would we see? Well, we see what gets drawn in every textbook, a bent molecule. So this bond angle between the two, or between the oxygen and the hydrogen is at 109.5 degrees, right? So that's why water is a bent molecule. It's dictated by those lone pairs. Something to point out here, so lone pairs actually take up a little bit more space than the bonding pair. So if I look here, this bond is actually a pretty tight little space, and this lone pair is a big, fat lone pair that sits on the top. Well, why do lone pairs take up so much space? 1, it's electron density, right? So it's a big dense region that it takes up. And 2, if we look at a bonding pair, we've got our protons that are in our nucleus of one atom. So maybe this is the hydrogen nucleus. And we've got our protons in the nucleus of the other atom. So maybe this is our oxygen nucleus. And when those electrons are shared between these two atoms, they're kind of stretched out or attracted to both of those nuclei. So that we see, instead of this big, huge, fat region, it's kind of more of a stretched out region. Where when it's a lone pair, there's nothing over here on this right-hand side that's holding that electron density tight. So this lone pair just kind of sits as a big fat blob on the side or the top of this particular atom. So lone pairs actually take up more space than a bonding pair. What does this mean for geometries? Well, what it means is that in an ideal perfect tetrahedral molecules with 4 things attached to it that are all bonding pairs, those bond angles would absolutely be 109.5 degrees. But when we have lone pairs in the mix, these lone pairs actually put stress on these 2 hydrogen atoms and push them or squeeze them a little bit closer together. So when we actually measure this angle here, it's actually 104.5. So slightly smaller because these big fat lone pairs are taking up all the room. Okay. So ideal tetrahedral, 109.5. 1 lone pair, we see a slightly smaller angle. 2 lone pairs, we see an even smaller angle. So this chart is something that I advise that you guys have close to you on the exam, and it's going to be provided in the helpful handouts. So if you want access to it, that's where you'll find it. But the key here is to know how to use it before you get to the exam. Okay. So most often students kind of eliminate or ignore this first column. It just kind of leads to some confusion. They really focus their attention on the lone pairs. So they'll look at a molecule. Let's look at this guy right here. Let's look at this molecule right here. So students will identify first the central atom. So the central atom here is sulfur. Then they'll decide what is attached to that sulfur. Well, I see 2 bonding groups. So this is 1 and this is 2. And then I see, let me just switch colors here. I see 1 lone pair. Okay, so 2 bonding groups, 1 lone pair. So they'll come over here and they'll say bonding groups, 2, lone pairs, 1. This is the geometry for that particular molecule. So electron geometry is trigonal planar. Molecular geometry is bent. Okay. So this is what I would ask for on an exam. I would say something like, draw the Lewis structure for sulfur dioxide or SO2. Tell me what the electron geometry and molecular geometry would be. Okay. So that's what it's going to look like on an exam. So that's going to conclude this lecture. Again, I would pause here and go practice. Practice, just like I said, Google Lewis structures. There'll be more worksheets with answer keys than you have time to do. Go to Chem 101, start drawing these structures. You can kind of twirl them around in 3 dimensions so you can see that the planar is all in the same plane and flat, and you can see that the tetrahedral has some lift to it. So I would advise you guys go practice with these molecules, because the next thing that we're going to talk about is going to be a pretty difficult topic if you can't picture these molecules in 3 dimensions. Hope you guys found this helpful.